Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is MIOR ASLAM bin ZAIDI. For today, I with my friends will present to you about the trajectory of multilateral wells and completion system design of Bilais well. So we got RODOLF in the house, AZLAN and ABDUL bin JAPAR. So without further ado, let's continue with our presentations. Okay, we continue with the introduction part. Directional drilling is a method used by oil corporation to gain access to subsurface sources of oil. Directional boring is another name for directional drilling because most oil wells are above the targeted reservoir. Okay, digging vertically from the surface to the well below. By 1953, a 9-branch well with barefoot laterals was drilled, despite the fact that operators recorded a 17-fold boost in output over offset wells. Beginning in early 80s, at standard rich wells have followed a similar path and continually developing. Alright, so digitalization, which encompasses a wide range of computer application at various levels, is a dominant contemporary focus in that sector. Okay, improved recovery is one of the key drivers, which means we must favor oil flow and manage or decrease water and gas output. Operators have been using simple ML wells since the 50s. They were using the technology in an increasing variety of configuration by 1997. And causing a group of operators and service companies to form a technology names which is TAML, which mean Technology Advancements of Multilaterals. Thank you.
Okay, my name is RODOLF SEVILLANO, and now I will continue with the selection and design of multilateral well trajectory. So, for optimizing performances, the trajectories of the lateral branches within the reservoir zones must be known when starting a well plan. It is required to know the reservoir properties, rock stress regime, and geometries of the productive reservoir units when determining the lateral branch trajectories. According to Bosworth and Elsaid, the kickoff point of the Bilais well is assumed to be around 1,000 feet and to 2,000 feet, and the build-up rate is assumed to be 2 degree feet. So we have done the calculation and we were able to generate the well trajectory as shown in the first picture. The other picture is a graph that shows the Bilais well is a stacked multi-branch well.
Okay, we continue with the case study. Case study 1 shows that according to the research by Bosworth, only multilateral well completion was documented between 80s and 1995. Since 1995, hundreds of multilateral wells have been built, with many more projected in the following years. As technology for drilling multilateral wells improved, the number of well rigs using this method continues to rise. The goal of this plan, which is referred as a stacked multilateral well, which stated in figure in my presentation, is to improve reservoir recovery, to increase production rate, increase output from the drilling zone by adjusting the slope and vertical depth of each drain hole. A large number of thin formation layers can be drained. While drilling an economic well in naturally fractured rock with an unclear or variable fracture direction, a fan configuration can be used to maximize the likelihood of encountering a natural fracture. For case study 2, we can see in my slide that the stacked multi-branch well in Zatco offshore field. Okay, so according to the study, which is one of the largest oil producing zone in Middle East and located in the Arabian Gulf, Abu Dhabi, has a stacked multi-branch well trajectory. Okay, it's the one of the most acceptable well path for horizontal drilling has been identified. In Zatco field, total of 85 horizontal wells have already been drilled. The use of a new directional drilling technique to drill multilateral horizontal wells that are multilateral with one reservoir, multilateral with traverse trajectory, and multilateral in different direction for the main well bore enable this rapid advancement in horizontal drilling at Zatco field. Because of the condition of multilateral wells that can be drilled in shallow and low permeability reservoirs that are opposite to the vertical well, these 3 approaches have been selected to operate in the Zatco field. Furthermore, by drilling the stacked multilateral from a single window, the zonal communication area can be reduced by utilizing fewer steerable drilling paths and components. Okay, we continue with the case study 3. The third case study is for stacked multi-branch well that is operated by Ecopetrol located near Bogota, Colombia, and the Castilla field of the Guadalupe Reservoir. Alright, so Ecopetrol was approved for field production in 2000, according to this case study by Mercado. And the first horizontal well was completed in February 2001. Later that, 7 wells were constructed to be drilled in directed pattern to improve reservoir exposure. Okay, then in 2006, multidisciplinary team was formed to evaluate the viability of the advanced well construction in order to increase oil sweep performance and avoid bypass oil in the K2 reservoir. Okay, in this field, the created stacked multi-branch well used the concept of building parallel trajectories of varying depth. It could be used to extract from a variety of reservoirs of the same interpolability of thickness and are sufficient to proceed with the adjustment. Thank you.
Okay, now we are moving on to the assumptions and justifications in multilateral well trajectory. So, based on the findings of all three case studies, the first assumption we made is the reservoir in Balais field is a thin, low permeable deposit. Given this, a stacked multi-branch well is the best approach to operate in this reservoir while maximizing output and lowering costs. This is because the stacked multi-branch well is able to give variation in inclination owing to the drain hole and vertical depth of each drain hole. As a result, several thin formation layers will occur, making hydrocarbon extraction much easier. For the second assumption, based on the information provided, the Balais well condition, we assume that the reservoir includes numerous wells and that the oil production rate is too low to support oil recovery. By establishing a single main well with branches, we can reduce the number of single vertical wells while increasing the number of stacked wells linked to the main well. Rather than drilling a new well, this method is far more cost-effective because of the higher well productivity and well development technique of stacked multi-branch wells. Rig time might be decreased while oil output is maximized. The firm will be able to produce more than expected due to reduced rig time. Next, we believe the reservoir at Balais has an aquifer. This is because when there is an aquifer, stacked multi-branch has the potential to impair water development. As a result, the primary sediment and water in the early phases of oil production will be delayed. As a result, when water development is postponed, oil and gas output might remain steady and have a few increments. Finally, we believe that reservoir in Balais field contains just a few cracks. This is because when there is a limited fracture, the productivity index is likely to be low. To improve its productivity index, the organization might employ stacked multi-branch well as a solution. The well will uncover additional natural cracks in the reservoir by using the stacked multi-branch well. The more production index rises, the more natural fractures are identified. The operation to extract additional oil from the producing zone will be able to continue if the productivity index is high.
Multilateral well completion necessitates the drilling and completion of many lateral boreholes in a single main bore. As a result, angled, horizontal, vertical, and extended reach wells require a separate well construction procedure. According to research by Bittencourt and Ladira in 2004, Alexander Grigorian invented multilateral wells in 1949, arguing that expanding the width of a borehole might boost oil output information. The current multilateral well enables the engineer to boost well output while lowering the expense of drilling additional wells by incorporating many production zones into a single well, or increasing the well bore's contact area with the formation. In our case, based on the well trajectory design drawing, we have chosen the stacked multi-branch well. Having branches in the production well boosts output, improves hydrocarbon recovery, and boosts the zone productivity. There are numerous lateral holes in a stacked multilateral well. Every one of them penetrates a single fruitful horizon. As an outcome, the system can generate two or more levels that do not communicate vertically. Drilling a lateral hole in each stratum allows for more exposure to formation for fluid movement in the wellbore. The evolution of existing multilateral technology has led to the technology advancements of multilateral TAML, identifying multiple levels of multilateral junctions ranging from TAML level 1 to TAML level 6. Based on assumptions and discussions, we have chosen the TAML level 5 for our multilateral well completion plan. Our selection is mostly based on reservoir characteristics, costs, and functions. There are various advantages to using a stacked multilateral well for oil productions. This approach, according to research by Permadi in 1998, has improved well production, slowed water enrichment, and reduced the number of wells dug. Oil can be produced from each layer separately via many strings or concurrently via a single tubing string via a one-way check valve below the connection to avoid cross-flow. The TAML level 5 system can achieve mechanical and hydraulic isolation without the use of cement at a multilateral connection. This method also allows for re-entry into both the main and lateral wellbore. Also, the pressure integrity offered by a TAML level 5 will prevent the commingling of the flow from the main bore and lateral flow. The TAML level 5 connector is insulated from the formation, allowing it to sustain drawdown pressure and avoid junction failure. The reserve recovery will grow and the well's output will improve. Based on the benefits of the stat, TML level 5 is definitely the best multilateral well completion strategy. Next would be the innovative design with suggested improvement. As it is totally isolated by hydraulic, the pressure isolation at the connection section is provided by completion string and packer. By using tubing and isolation packers, this level may maintain high pressure integrity at the connection. Some issues may arise, such as the need to preserve the isolation zone between reservoirs. Siemens slurry can be utilized to do exactly that. This is because it will react with the hydrogen sulfide, resulting it to swell when injected into the borehole. It will harden based on characteristic of the hole. By doing this, the reservoir's isolation zone will be maintained. Recommended upgrade to our current revolutionary design for this segment will be the Rapid X TML5, a high-strength hydraulic-sealed multilateral junction from Schlumberger. This innovative technique has shown to be a dependable method of gaining access to oil and gas reserves. The Rapid X TML5 provides maximum reservoir contact, faster time to production, and greater flexibility with reduced expenditure.
So for the case study for multilateral well completion, there are 3 case studies, which is first is the first intelligent multilateral TML level 5 wells in the Villanovsky fields are an excellent illustration of how contemporary technology may help with the capital expenditure optimization by obtaining greater production rates due to a higher productivity index. And for the consequence, Lukoil successfully constructs 2 of the first intelligent TML level 5 completion on the Villanovsky field, producing 20% to 60% more than surrounding single bore wells, which is up to 38,000 barrels per day. So for the case study number 2, Halliburton team up with the largest North Sea operator to install multilateral technology (MLT) system in the Norway deepwater oil field. And this technology has a proven track record of success and industry-leading reliability. And for the third and the last case study, Chinese operator with a goal to optimize yearly recovery of oil while containing the reserve and production, and also keeping the gas production rate at 500 million cubic meter per year, set high level 15-year output target for a large oil field with a low average oil production. And the successful performance of Rapid XTML also proves that it can be employed in more application. And for discussion, for the multilateral well trajectory, we assume thin and low permeable formation at the target point. And the Blythe field has a stacked multilateral bench trajectory. The system is an excellent choice for increasing oil output while lowering operating costs. Fortunately, a stacked multi-branch well design helps relieve the problem by reducing the number of vertical wells in the field. As a result, it is wise to use stacked multi-branch well based on the assumption. So for the multilateral well completion, the level 5 connection of multilateral well, the ML level 5 offer mechanical and hydraulic isolation based on the well completion design. And to improve the well performance, Schlumberger Rapid TML5 has been advised. And this process is simple, yet it has been demonstrated to be effective in the production of new oil gas deposit. And as a result, calculating the hydraulic isolation at the junction is crucial for keeping water out from the lateral, even if the TML level 5 is more effective than other levels. But it is a good idea to install, since it will improve the operator financial return of drilling and wells completion in the future. And for the conclusion, the technique of well completion is determined by the targeted potential hydrocarbon, and it's crucial to understand which type should be utilized and what assumptions should be made about which type. And for the multilateral well trajectory, we choose the stacked multilateral wells, and for the multilateral well completion, we choose TML level 5 for the design. Yeah, that's all from me. Thank you.